Relativity. What does the word even mean? It means everything is relative. But what does that even mean? It means things can be different depending on how you're measuring it, where you're measuring it from. What kind of things can be different? Well, the answer is time, length, mass. Those things can be changed. They're different if you're measuring it when you are stationary, and they're different when you're measuring it when you're traveling near the speed of light. That's pretty confusing. But relativity is really essentially just four equations used over and over in exams, in tests. Four equations. Well, the first one is the Lorentz factor equation, and that's the one we have here. It's not yet completed, but it's 1 over square rooted 1 minus v squared over c squared. Now, v is the velocity of the thing that's traveling, because relativity only, the effect of relativity only shows when the speed of the object traveling is near the speed of light, like 50% of the speed of light. While our satellites, the fastest moving object humans have ever created, is probably satellites, right? Man-made subjects, satellites. They move at 10 kilometers per second in space, very fast stuff. But compared to the speed of light, which is 3 times 10 to the power of 8 meters per second, that speed is still too slow for the effect of relativity to really show up. So, without further ado, if the speed of the object traveling is 0.5, 50% of the speed of light, you can just fill in 0.5 times 3 to the power of 10, 3 times 10 to the power of 8, the whole thing squared, over 3 times 10 to the power of 8, the whole thing squared. But when we do that, we notice that there is some overlapping, 3 times 10 to the power of 8. So we simply just cross out 3 times 10 to the power of 8, leaving us with 0.5 squared. So that just becomes this, really, 1 over 1 minus 0.5 squared. And that's an easy trick we use when doing this sort of calculation, because the speed is usually given to you as a fraction, as a percentage of the light speed. So that's really convenient. There you go, that's the first equation. The second equation is time dilation. So that is this, T equals Lorentz factor. So we calculated the Lorentz factor using the first equation, and using the Lorentz factor, which is this Lorentz factor, we do the second calculation. T equals Lorentz factor times TO. Well, we need to know that Lorentz factor is always bigger than 1. This is always bigger than 1. When you time a number by something that's bigger than 1, the product you get is always going to be larger than this number. So we know that now T is always larger than TO. So how can this be put into practice? Well, let's say a spacecraft is traveling near the speed of light, right? Very close to the speed of light. Now, the time of its traveling measured from someone on Earth who's not traveling near the speed of light is going to be, say, 40 seconds, right? But the time measured by someone on the spacecraft is going to be shorter than the traveling time that was measured on Earth. Take a minute to absorb that knowledge, because that's quite confusing, right? Time is not constant everywhere. It's different depending on where you're measuring it from, depending on how fast you're traveling. So In the reference frame of someone measuring on the spacecraft, the time is going to be this. The time for them is going to be TO equals T over Lorentz factor, right? So for me on Earth, that traveling time could be 40 seconds. But let's say the Lorentz factor is 2, right? The traveling time in their reference frame is going to be 20 seconds. So in summary, when you get faster, time gets shorter for you in your reference frame. Length contraction is really similar. Now length contraction is L equals LO over Lorentz factor. So you're dividing a number by a number that's larger than 1. This means L is always going to be smaller than LO. So now the word length contraction just means get shorter. So when you get faster, um, in your reference frame, everything's length is going to get shorter. So L. So in this case, if I measured 40 meter, if I'm looking on Earth, someone on the spacecraft measuring the same object is going to measure a shorter distance than that. So now, say LO, me measuring, let's say, a building on Earth, right? It's 40 meters tall, 40 meters, and the Lorentz factor is 2. Well, for this person looking out and measuring this building who's traveling near the speed of light, their um, the length that they measure is going to be 20, which is shorter than what I measured. So that's called length contraction. Length gets shorter. And the last one is not as confusing as the first two because you just fill in the numbers. Pretty easy to see. This is a momentum, relativistic momentum. P equals a Lorentz factor again, MO, which is the mass of an object when stationary, and the V, velocity. Lorentz factor is always larger than 1, and you time this by the mass of something when stationary, right? So if I'm 73 kilograms, big boy, and I'm traveling near the speed of light, or somewhat near the speed of light, and the velocity, yeah, v equals. What you're going to see is that the momentum of me when traveling near the speed of light is going to be larger. It's going to be large, right? Because of Lorentz factor. And actually, the faster you go, the larger your momentum will be. That means the faster you go, the heavier you will weigh. That's pretty weird. Anyway, this is relativistic momentum. Don't really need to get into it, but there you go. That's the equation. That's what you need. Easy.